So once again, let's continue with the discussion of kinetics. We're going to follow through where we left off last time. Now that we've discussed things like reaction rate, we've discussed ways of actually defining the rate equation. We can measure it experimentally. We now know some concept of what K is and where it comes from also, because last time we discussed the reaction trajectory or the reaction coordinate, right? This is the path or the free energy change of a molecule as it undergoes a bond-forming event. So we describe this in a different way. Remember, we have two different ways of visualizing our sort of reaction versus time. If we're talking about our free energy, G, versus extent of reaction, this was previous. This is what we talk about in thermodynamics. The extent of reaction is what we're plotting here versus what we did introduce last time, free energy versus coordinate. Again, we're discussing two different things or two different ways of sort of visualizing our reaction. We're always going to start with some starting state. We go to a final state. That's our starting material to our products. When we're discussing extent of reaction, what do we call this value right here? Delta G naught. Yeah, this is the delta G naught of reaction. That's the same thing over here. The change in free energy, talking about going from starting material to product, the overall point, it's still an energetic expression, which talks a bit about favorability, right? We talk about if a reaction wants to become that product. We anthropomorphize things. This is downhill in energy. In both cases, we're expressing the same general concept. So the value difference is true in both cases. That's our delta G naught. On the extent of reaction profile, we're talking about how free energy is minimized as it is approaching equilibrium. So we have this sort of tie line. We usually look at this in terms of, okay, right here, this is our delta G for a process. The overall part here equals 0. That is our point where we say we have reached equilibrium. And we can look at this in terms of a compositional diagram, a population or a ratio of starting material to product, and talk about, are we at equilibrium? Do we need to move forward or back to reach that equilibrium? So it's a compositional idea. What we're talking about now, in terms of coordinate, is the energy barrier that a reaction will experience, a single molecule, as it undergoes bond exchange, breaking bonds and forming bonds. So it's a similar concept, except think of it where we're talking about the individual in terms of the coordinate versus the population for the extent. We defined this value here. What is that? Going from our starting material to this apex, we call that value something special. That is delta G double dagger. It's the free energy of activation, or think of it as the speed bump to a reaction. This is why reactions have K values. If we have a really big speed bump, we're going to have a very fast or slow reaction. Which is it? Slow. Big speed bump, slow reaction. Small speed bump, fast reaction. What does that mean for the size of K? If I have a really big speed bump, big K or little k? Little k, because remember, K is directly proportional to reaction rate. If I have a really big K, I have a very fast reaction. If I have a very, very small barrier, I will have a very large K value. Those are inversely proportional. A big barrier makes your reaction slow, which also means the K must be small. A small barrier, reaction's fast, very large K value. So this here is where we mathematically can derive or actually measure K, or K can tell us about that magnitude, the energy that's there. What do we call the species which exists right there at the apex? That's a special thing. We call it the what? 2 words. It is the, starts with a T, second word S. It is the transition state. It is a theoretical construct. Basically, the molecule must move through that point. It is an arrangement of atoms and electrons that must exist. You have to walk through that point, but it is transitory. In other words, you could never put it in a bottle. You cannot freeze it. You cannot hold onto it. It is something that happens only in an instant. So my demonstration yesterday, last time, climbing up on the desk, if I can hang out there and I could freeze there, stay there and wait there, that is an intermediate. It is something that has lifetime and I could pause there. Even if it's high in energy, it can pause. If I jump off the desk as I'm moving through flight, unless anybody snaps a picture with your cell phone, that's transitory. It does not exist beyond the moment that it happened. It is not something I can freeze time and stop midair unless it's a Ferris Bueller's Day Off kind of a thing or whatever. But transition state is something you do move through but does not exist for a lifetime, right? It's something here. This is our transition state. And what its structure is defining where that barrier is. Certain transition states are very high in energy. They have very high barriers. It takes a lot of energy to reach them. But that's how we define or describe this sort of system. So we left off last time talking about bringing these two pieces together, the concepts now of our path, our transition state, these rate concepts, and bringing them back to elementary steps. Knowing something about the rate equation starts to teach us about these individual things. And if you remember last time, what was the answer here? If a reaction, A plus B to C, obeys the rate law, rate equals K, that's our rate law, which is true. So everybody, it was E, that's right. What is the order of this reaction or process? This is, yeah, it is a zero order process because there are no concentrations in our rate equation. Rate equals K. That is the observed rate behavior of this system. Now let's take apart each of these. If I said the half-life will increase with time, what order or what process obeys that statement? Remember back to half-lives. Yeah. Yeah. First order, does first order change with time? First order half-lives are, yeah, they're constant. So that's, if we said half-life was constant, we're saying it's a first order process. That's the sort of decode there. Half-life will increase with time. That is a statement which is true for second order processes. The reaction is bimolecular and elementary. How would that be true? If you look back at your rate equation, what must be true for that statement to be true? What should the rate equation be? What's that?
A squared.
A squared or A plus B or AB, right? You need two things. It better be second order. And for it to be, that means the bimolecular part, right? To be elementary, what do we need to be elementary? Basically what we can tell for now, if the rate equation looks like the reaction, it could be elementary. This is the reaction. This is the rate equation. They don't look anything like each other. There's no way that reaction is an elementary process, an elementary step. A plus B going to something else where the rate equation is zero order, we don't have any concentrations in A or B. So that's wrong. A plot of ln A versus time is linear. What is that a statement of? What kind of process are we talking about for that? Ln A versus time, zero, first or second?
First.
Yeah, this is a first order process. A plot of ln A versus time, that comes from our integrated rate laws. This is a statement of a first order process. The reaction will be slower when the concentration of C is large. What's wrong with that statement? What is C in this process? Starting material or product or intermediate? It's a product. Real products of one-way reactions affect the rate. No, they shouldn't. They're made and that's done. We're done with fuel. Since C is not a fuel, this should have nothing to do with the reaction. There's no statement where the product right now, up until what we've talked about, product should not affect the rate. That one's out too. The reaction cannot be elementary. That is what we conclude from this. If you look at the rate law and you look at the reaction, they do not match up. That's what we're putting through. So, now that we're talking about multi-step reactions, we can use kinetics to derive what the mechanism might be. And from that, we can validate a mechanism. Basically, if I observe how a reaction behaves experimentally, I solve that the rate law is something using method of initial rates. I can then propose a mechanism and say, does this mechanism fit, yes or no? So we're doing an exploration on one side, saying this is how the reaction could occur. And then from that, I can say, if this is the mechanism, and I make a couple assumptions, what should the rate law be? I look against my experimental and I say, do these two match? This is a way of validating, saying, ah, yes, this proposed mechanism is supported by my evidence for how the reaction may occur. That's what we're going to walk through right now. So if you look at this, and if we just take this, again, this could get really complicated. Lots and lots and lots of individual steps. In general, if we have a simple two-step mechanism like this, and we're asked to solve the rate, The answer is it kind of depends, and it depends on what happens between these two steps. We know it's an elementary process if it passes through only one transition state, but you can chain together multiple elementary processes. So in the expression we just showed last time, if I start with the reactant, if I move through one barrier and I go to a hollow, a low energy position, that is my intermediate. I've done a step, I've gone through a barrier, I take a breath. I stay and I wait. Then I have to get ready and I do another step. Second step has another delta G naught value. And the delta G naught, in both cases, you can sort of decompose it and look at the first step as just this individual piece. So you can focus on this as just a process unto itself. It has a delta G naught, it has a delta G double dagger. So it has an activation barrier, but you can also talk about just this energy here. So you could, if possible, you can set up a reaction to only look at that one step. Now, depending on how much energy is in the system, what's involved, it may not wait there for very long. It may pass through this. If this reaction was run at the right temperature, that intermediate could fly through that first barrier, sit there and wait for a second, and then still continue on its journey, now with a second activation barrier, delta G double dagger, and a delta G naught here for that just second step. Normally what we would do is focus on just this value. This is still our delta G naught reaction, the overall energy difference between reactants and products. But we can use the individual steps as a way of decomposing and sort of saying, well, based on this, what do I expect to occur? As this diagram is laid out, which of the two steps do you think is faster or slower? Is the first step fast, or is the second step fast? Okay, first, why? That's it, smaller hill, first step is fast. What that means is kinetically, if we measure, put a clock on this, the second step is more important. It's going to be the one that's really driving the bus. Now, the first step may still play, depends on the magnitudes, but this is how the aggregation, the rate we observe, will now depend on what these values are. Which one's big, which one's small, how many steps and how many intermediates you have. That's the mechanism. So there's a predictable sort of mathematical form that will arise based on what this looks like. Just looking at the rate law on its own, we do not know. We can't say, that rate law means this is definitely the energetic surface. We've got to combine a little bit of experimental to pull these two things together. So we're going to consider two different variations. To keep it simple, it's these two extremes. The first case, a two-step process, where the first step is fast, second step is slow. The second case, first step is slow, second step is fast. And just those two. And there's experiments and examples of both of these ones. These are very common. A lot of the reactions fall into these kind of categories, right? These are the ones we can start off with. So, if you had this, though, where do you think the rate limiting step would be? Well, chat it out. Turn to your partner, turn to whoever's next to you. Which one is your slow step? Which one do you think is driving the bus in terms of the kinetics here? A, B, C, or D? Or E? Okay. So for consensus, I want everybody all together, same thing, give me a letter. A, B, C, or D, E. This is? A. I agree. The first step is the one that's driving the bus. So think about it this way. The first step is your barrier. The first step is the slow step. After that, what do we say about all these relative to A? They are what? Faster or slower? Faster. So this is, what do you think about the rate law of this? If A, the first step is driving the bus, and we knew everything about how A worked, does it matter after that in terms of what those rates are? Will that control or slow down the rate anymore? No, probably not. This is a traffic analogy. So who here drives to UBC campus? Okay. Have you ever tried to leave Marine Drive at like 5 o'clock? Yeah. And okay, I'm a broke prof. I drive a very, very old Honda Civic, but I see some people leaving campus and they have the most beautiful Ferrari F-150. Do you think, that's wrong, sorry, McLaren F-150. Do you think it matters how fast that car is when they're trying to leave Marine Drive at 5 o'clock? So it doesn't matter after this step, this is your horsepower. This is how fast the reaction could be. It doesn't matter how fast it is later. If your barrier is now, the thing that's going to control how fast you get off campus will determine how fast the rest of your ride will be. So this first step is completely controlling how fast this moves, right? So that's the sort of image to take into it, is it really is like a traffic jam. If you have a barrier of sort of how fast you will go, then it is going to influence everything else after it. So this is how we use the kinetics or the rate law to determine what's going on in the mechanism. Understanding where that barrier is and what the mathematical form is will sort of express the two. So in our first example, we have a slow step followed by a fast step. And we just talked about that example. The slow step will control the process, which means if I have a two-step reaction, A has some rate constant K to make my intermediate. Second step, that intermediate has another rate constant, little k2, to make our product, B. What do we know about the magnitude of these two? Which one would you expect, based on the diagram, to be big and which is small? Slow step is first. What does slow mean for size of K, bigger or smaller? Small. So which is smaller, K1 or K2? K1. K1. That's the one that's going to drive this whole process. If K1 is small, we look at this overall reaction and we can say, look, I can, for an elementary step, I can write the rate law, right? I cannot look at the overall reaction and say, oh yeah, by inspection, rate equals K times A. What I can do is say that I have some first step, it's an elementary process, so by inspection, I can write its rate law. The rate of the first step is equal to K1 times A. Now, the second step is also elementary process, which means that one can be written as well as the rate of the second step, or rate 2, is equal to K2 times intermediate. And that's great. These are two individual elementary steps, which means I can talk about each of them by inspection. I can write out their rate equations. Again, that's just by looking at starting material concentration and the rate constant for each step. The problem is, that means that this first step is what we call the rate determining step. The second step doesn't matter. The second step is not part of what's going to determine the overall rate of the process. I can now say that, okay, this guy here is the one that's driving the bus. It's the one that's overall going to control how fast this process will go, just like the question we just talked about. If this is our first step, we can say that the overall rate really can be approximated simply as that first step, K1 times A. After that, any fast process that we're going through will not have a major impact in the overall rate of product formation. Those are all after what's holding the step back, our speed bump. So the nice thing about that is we now have a way of, as long as this first step is slow, I can say that that will be my rate determining step. If this is my rate determining step, the corresponding rate equation can just be done by inspection of the first step in whatever overall this mechanism is. And remember, there's a couple correlations here we want to emphasize. If the rate of the first step is slow, there's a couple of ways of talking about that. Remember, slow first step, we say that either the value of K, so the magnitude of this rate constant, must be very small, right? A small rate constant is synonymous or means the same thing as having a slow rate. It also means that the time of that first step will be longer than the time of the second step. So there's one way of expressing that. So look at this question. Overall, what we're looking at here is saying that, look, I've got a two-step process. In this two-step process, the radioactive decay is a first-order process, which means it can be described as two individual elementary steps. So thinking about this, what do you think the right answer is? What's the right statement to go through here? So this is an expression where what we're saying is if I can separate these two, and we've been given information not about the size of K, but about the half-lives. In this case, the first half-life is very, very long. The second half-life is very short. In other words, which is the slow step, the rate determining step here? So everybody all together? Does that make sense? A is your one. Why does that happen? If you look at your first step, the mechanism says in this first decay, the half-life is a lot of years. Second step, couple of days. Which is the slow step, first or second? First. And again, if we're saying that, if the first step is slow, long time means what in terms of rate? Lots of time, big rate or little rate? Little rate, right? A little rate like that, yeah, a little rate like that means that the K value must also be small. So K and rate are directly proportional. How much time you take and the barrier are proportional. Very big barrier, little rate. Very big barrier, long time, right? So those are the two sides to sort of look at how this, this disposition goes. So that's the first one. That's the easy one. If the first step is slow, you can look at the first step by inspection. You can derive the rate equation based on that first step, and that's it. The entire rate equation is just saying mechanism the first. Now the second one is where things get a little bit more complex. If the second step is slow, what happens here is you've got sort of a shot on goal, but it does not go to completion, does not go to product. Shot, product, no, back and forth, back and forth. This first step is what we call a fast pre-equilibrium. The first step is not rate determining, you need it, the reaction will not go to product without it, but it's the second step that matters. This is, again, this is something like you keep taking a shot on goal, you have to get into sort of that position, but it will not, you're not actually scoring that goal until you're in the exact right point. The rate limiting step is that second position or that second shot, which means this step number 2 is the one that's driving the bus. So once again, if we're going to do this and draw this out, same position, we say the first step is fast. Okay, that's great. That's not rate determining. The second step, intermediate going to product, that's my rate determining step. And its equilibration, or its formula is rate of number 2 is equal to K2 times intermediate. That's definitive. There's nothing wrong with that, that yes, I know the rate of the second step is K2 and intermediate. The problem is I don't always know what the rate of the intermediate is. So in the same way the first step is whatever the rate determining step is what defines what the rate equation should be. The problem here is since the intermediate is something that is generated, it's fluxional, it's constantly changing, it's difficult for me to actually drive a rate equation there. So there are two simplifications we must use in order to deal with this. The first is we say, okay, look, I don't know, I have no expression for the concentration that's intermediate. But I do know something about what it should be based on the laws of the actual sort of system. So the first I can do is say, look, if I know the first step is what gives me this intermediate, and the first step is an equilibrium, I have an equation from back in thermo to express the concentration of that intermediate. Remember, if this is an equilibrium, every equilibrium can be described in terms of an equilibrium constant, capital K, not little k. And that's products over reactants. So if I know that this first step is a fast equilibrium, I can say, well, look, any equilibrium can be expressed in terms of a capital K value, its equilibrium constant, and products over starting materials. Right? That's a thermodynamic statement. The thing we're assuming if we make this statement is we say the reaction, the first step, exists in equilibrium the entire time as the reaction is happening. I'm just going to assume that it is always in equilibrium, which means that first concentration obeys this capital K rate constant. We're assuming that first step always maintains this equilibrium position. And that means I now have an expression to get me to my intermediate concentration. This value, how much my intermediate concentration is, can now be solved just by rearranging my equilibrium equation. It's capital K times starting material, right? And this is good. I now have a constant, capital K, and I have my starting material. This is now something I can use to sub into my real rate equation. Since the real rate equation bases on that second step, it's K2 times intermediate. However, since I don't know, this is an unknown, I make an equation or term to express that, and I sub that value into my concentration intermediate. This looks like, if you remember back, when we did pseudo first order equations, this is kind of what we're doing. I have a rate equation which has an unknown. concentration intermediate. I define something that I do know, my concentration A and my equilibrium constant. What that means now is that these two, since these are both constants, I now get what's called a K observed, a little k observed. It's just the multiplication between K2, the second rate constant, and capital K, the observed, or the equilibrium constant of that first step. Since they're just constants, we multiply them together and we get this K obs term. This is now what the actual rate will look like. It's not exactly the same as the first step because we're taking K2, that rate constant of the second step, and this equilibrium constant, capital K. By multiplying those magnitudes together, we're going to get a value. The rate will depend on that equilibrium constant. So think about that for a second. If I had, let's say, a weak acid, what do we know about the value of capital K, equilibrium constant for a weak acid? Big, small, bigger than 1, less than 1? Less than 1. If I need to use A minus, the product of that ionization, the reaction's not going to run unless we have A minus. So if I have a weak acid, I have to dissociate to make my A minus, and then A minus is used in another step. If I have a weak acid where it's almost 100% starting material, the rate's going to be really small. It's basically going to be restricted or strangled by waiting for this A minus to show up. However, if I have another weak acid, which is still starting material favored, but there's more product, reaction is going to be faster, even if that second step has the same magnitude. Since the second step needs K2 times intermediate, and if you restrict this concentration of your intermediate, it still holds the reaction back. So that's why the two of them add together as a product. That's what we get with this K obs value. So that's the first one. Okay, so we have two examples we've covered. First step is slow. Life is great. Know the mechanism, look at the first step, derive the rate equation according to the first step. And we're done. Second example, we have a fast pre-equilibrium. We assume the first step always obeys equilibrium. We can express their concentration in terms of K times product over starting material. In which case, we now have an expression for intermediate, that's in our second step, and we can derive a rate law with that capital K value as part of it. Awesome. The third, more general way leads up to what's called the steady state approximation. For this one, we make one more jump. We say, look, it's still in equilibrium, but it doesn't have to obey equilibrium. The capital K value does not need to be the same for the entire course of the equilibrium. It can exist slightly outside of equilibrium, but the thing we say is an equilibrium, by definition, means that the forward reaction and the backward reaction are balanced, right? That if I go faster in one way, I also go faster in the other way, and the overall concentration does not change. So if we view an equilibrium process, instead of thinking of it now as A is in equilibrium with B, decompose it into this here. A in equilibrium with B is actually a two-step mechanism. We actually think of now A in equilibrium with B is actually step 1, A goes to B, and step 2, B goes back to A. We look at them as two individual, distinct elementary processes, one forward, one back. Now, why we do that is because now, instead of talking about this in terms of capital K is our rate constant we use here, I have what we call K1 and K minus 1. That's these two rate equations here. We look at them in terms of small k rate constants. So now what we've said is, okay, I'm going to view all equilibria as simple elementary steps. And all I'm saying is I'm at equilibrium in the kinetic sense if the rate forward equals the rate back. That's what we state here down at the bottom. Rate in one way equals the rate backwards. That's our definition of equilibrium. And what I know is, since the rate, based on our two processes here, this is the rate constant for a forward reaction, this is the rate constant for a backwards reaction. It's made the same way by taking our two individual mechanisms right here. Since I've got mechanism 1, it's concentration A and K1, and concentration B, K minus 1. That's how I derive these two parts right here. Yes?
K1 and K minus 1 can have different values.
Totally different values. That's basically, all we're saying is K1 and K minus 1 are still still rate constants. If K1, forward one, is really, really big, and K minus 1 is very small, what do you think the value of that equilibrium constant will be? Is it product favored or starting material favored? If forward is a lot bigger than backwards, is this a product favored equilibrium or starting material favored? We're just saying the rate to get to product is much faster than the rate to starting material. And why it balances out is, at some point, there's very little starting material left, in which case there's tons of product. Even if the K-1 is small, it still balances out. So this is a product of both the constant and how much you have. At some point, you may have a very small K, but a very, very, very big concentration, and they equal each other. One and the other can sort of equal out. That means I can express this equality here as my normal canonical rate equation, my normal equilibrium constant. All we're saying is we've got this new way of defining. Capital K, we talked about before, was concentration of products over concentration of reactants. When we're talking about it in terms of little k's, capital K can be decomposed into the forward rate constant, K-1, little k-1, divided by the backwards rate constant, little k, little k1 over little k-1. The ratio of the two microscopic rate constants is exactly the same value, magnitude, as our capital K value, the equilibrium constant. So all we've done is decompose what we normally use as our K value into two small k values. The capital K equilibrium constant is now expressed in terms of the two little ones. So this is now just, again, we're just visualizing the reaction differently. Instead of saying, well, equilibrium is just everything's going back and forth, we're thinking about them as two discrete steps tracking the population of individual molecules. We have a forward reaction and a backward reaction. We have mechanisms that sort of think about both. In this way, you can think of now, instead of being a two-step process, equilibrium and second step, it's kind of like first step, the equilibrium, is two individual reactions, one forward, one back. And the second step is our going to product step. We're decomposing it into three overall steps. So we say, okay, overall, what we have now, I have step one, it's this forward-backward process. Remember, that's two steps carried in one. And we have our second step. Intermediate goes on to product. That's the product-forming step. If this is still a rate-determining step, we now have a way of describing what the intermediate is doing. From the perspective of the new intermediate, there are three individual steps that actually balance or matter on this one. Excuse me. So look, if I take the forward rate constant, A going to intermediate, we are forming intermediate with that step. That's this one right here. So we say that, look, if I just want to watch, how does just the intermediate change with time? Not the concentration of intermediate, but how does the intermediate change over time? Well, there's three things involved. I form that intermediate using this first step here. That's K1A. I use up the intermediate. Here, that's the reverse reaction here. That's going backwards in this direction involving K-1. And I use up the intermediate going on to product. That's this third step here. So using up the intermediate here. So what I can express is the rate of change, how the intermediate changes. It's going to be formed using the forward, K1. It's going to be used up, K-1. And it's going to be used up going to product. So I have these three terms that now express just what the intermediate is doing. The reason why there's three is because it's in the center of all three of these reactions. It's generated, used up, and going on to product. So okay, that's great. We have a mathematical expression that talks about these three. This is where we make the next jump and say, I'm using what's called the steady state approximation. The steady state approximation just says, look, things are crazy, but I'm going to assume that this here is equal to 0. Not that the intermediate concentration is 0. That's not what we're saying. We're saying that whatever intermediate is there, its relative change or its concentration over time remains constant. The d intermediate, dt, the rate of change of intermediate, is not changing. So if we have these two, the formation in our step one, we have the two consumptions in step two, we're saying that everything has to balance. That those rate constants must be such that the concentration of intermediate is held constant as this reaction runs. Now what that looks like in terms of the reaction profile is like this. A is going away, product is coming in, but if you look at the intermediate over time, it's kind of staying level. So we're making an assumption that in this time right here, the concentration of the intermediate, the rate of change of that intermediate, d intermediate dt, is equal to 0. So we're not saying that there is no intermediate, we're saying it's a straight line with respect to concentration. There's a statement here, and again, this is a point. What do you think we'd say about this part of the equation and this part of the equation? Does it obey the steady state approximation early, right at the beginning, or very late at the end? Is the intermediate concentration constant in those two parts? Very beginning, is it changing? Yes or no?
Yes.
At the end, is it changing? Not as much, but it's still changing. Why this is important is the steady state approximation is something we say about the average or middle of the reaction. That's where it really applies. It's true as long as this line is not changing, but we know it has to, at some point, intermediate must build up. At some point, there's not intermediate left. Again, this is an assumption we have to make because outside of these areas, this steady state approximation is not valid. It's just like the buffering thing. If we have very, very little A minus or very, very little HA, we do not have a buffer. We break the Henderson-Hasselbalch equation. But it applies in the nice squishy part in the middle. So the statement here is saying, look, most of the reaction, that is true, and that's where we're going to use this approximation to learn about the reaction. It's in the middle part of the reaction. So the things I want to point out here is, first of all, making this statement, d intermediate dt equals 0 does not mean there is no intermediate. It just means it is constant or not changing with time. Second thing, steady state applies in the sort of heart cut, the 80% in the middle. Not right at the very beginning, not right at the end, right in the middle. And that's where we can use the steady state approximation well. Outside that, we get what's called terminal kinetics and initial kinetics. And again, come back and see me in 2 years. I'm happy to teach you about that. So now that we've made these two things, number one, we've created an equation to talk about how the intermediate changes with time, d intermediate dt. And that's done by looking at the mechanism and saying, how do I form intermediate and how do I use up intermediate? I need one term, a big, long expression that talks about that. Two, I then have to make the steady state approximation. I set it equals to 0. So the math looks like this. Step one, we take the overall process and I draw or I write the rate equation with respect to the last step in whatever this mechanism is. Remember, in this overall mechanism, we say that even though the first is an equilibrium, the second is our rate determining step. I said that, look, the rate is equal to that final step, intermediate times K2. So I have an overall, what we're saying here is rate, this is really saying change in product, dB, dt. And that's the thing we're really trying to focus on. How do I make product over time? That's this first step. Second step, okay, I don't know what the concentration of intermediate is. I am going to write an equation describing how intermediate may change. I look at all the steps that are involving that intermediate. It is formed, intermediate is formed here, K1A. It is used up, K minus 1 intermediate, and it is used up, intermediate K2. So we have three, let me actually match those colors. Boop. So formed, K1A is here. Used up, going backwards, intermediate in K minus 1, that's this one here. And forming product, minus K2 intermediate. And again, you can tie them off. The sign of it means it is being used up or it's being formed. And which one or which step it's involved with comes down to what the K value is we're talking about. So K positive 1, that's the forward reaction. K minus 1, reverse reaction. K2, that's moving on to the product. And the concentrations for each are associated with whatever that mechanism is. Okay? That's step 2. We then say, look, all of this, the rate of change of this intermediate, the steady state approximation, says that that expression must equal to 0. As soon as we do that, I can now algebraically solve for the concentration of my intermediate. This is that expression from the last page, that the change in concentration over time is equal to 0. I rearrange this and solve this for my x, my unknown, my intermediate. And I get this expression here. It's now a fraction ratio of concentrations I do know and the rate constants I'm trying to solve for. What this one here looks like will completely depend on the mechanism. Since as we go back, these steps are common no matter how you apply the steady state approximation, but depending on how many intermediates you see or what is involved in these steps, the physical terms may change. We'll go through another example of that as we go through. But step 3, we've now got an expression that talks about our unknown. I have a value or an expression to talk about x. I take that x and I go back to my first step. This was the rate equation I started off with. Rate was simply equal to, remember, product over time is just this second step right here. Since I now can sub in my intermediate, that's this whole value here, all of this is just all of this. I drop in that equation. It's an ugly fraction. All I'm doing is multiplying my K2 by this. It shows up now as my numerator. This is now what we call the steady state rate equation for this mechanism. And it looks kind of weird. In this case, it's K1 times K2 times A over K minus 1 plus K2. This is what's called the 1 plus form of a rate equation. But you notice, what do you see here? Constant, 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 variable. Right? What this means is I can sort of think of this as rate is equal to weird constants, K obs, times the concentration of A. Where this K obs is really just, oops, oh, come on, don't fight me. K obs here is all of this stuff. It's all the K's as whatever fraction it looks like. I'm just factoring out the A from the numerator. And that kind of looks like that first example we talked about, right? When we said if the first step was slow, it's just K obs, or sorry, second step was slow, and we said that the equilibrium was constant. That was just kind of what we were dealing with. This is just a little more complex version of it, and this is also the mathematically more correct version. So we can apply this generally to any system. This is a new reaction, new overall reaction. 2 NOs plus Br makes 2 NOBr. We have a mechanism. 2 NO has a K1, a K minus 1 to make N2O2. What is that? Intermediate, product, starting material, catalyst? Intermediate, because in the second step, first of all, it's not in the overall reaction, and we use it up to make our products. Now we're going to apply the steady state approximation. We're going to work through this. Now why this matters is we use the same 4 steps, but if the mechanism is different, if we have different terms, notice the example we did before was just simply A to intermediate, intermediate to product. 3 simple things. Here we've got a bimolecular elementary step. We have a bimolecular elementary step. This is more complex. So the form will look very different. So that's what it ends up looking like. Step 1. We look at the last step of the reaction. We write a rate law. So going back, the last step is right here. It is N2O2 reacts with Br2 according to K2. I could say that second step is rate is equal to K2 times N2O2 times Br2. That's the true statement for how fast product will show up. The problem with this is an intermediate. I can't leave it like this because I have a concentration of an intermediate that I must express differently. This is where we have to invoke the steady state approximation. We use that first step to give us that equation. All right, step 2. Sorry. There we go. I write d intermediate dt. How is it formed? The first step is N2O2 reacts together according to a second order rate constant to make product K1, or sorry, to the intermediate, K1 times NO squared. It is used up according to 2 steps. The reverse reaction minus K1 And it only involves the N2O2, and it uses up, according to the product, minus K2 times N2O2 and bromine. We set all of that equal to 0. That is the expression of our steady state approximation. Then we take that term, rearrange it, solve for x. Remember here, this is our intermediate. That's the piece we're trying to get out here. So when I rewrite this, I'm arranging this algebraically so that I isolate the intermediate I don't know. I get a new fraction. The difference here compared to what we did before, it's still going to have the same kind of form of a bunch of rate constants over a bunch of rate constants. But notice this one, because we had different terms, there are these other concentration profiles in here. What happens is, you can think about it this way. Anything that appears in the numerator will help to drive the reaction forward. Those are things that are usually on the way or moving forward in the overall process towards product. Anything in the denominator will push the reaction backwards. It is involved somehow in slowing the reaction down. So it's involved in one of those steps in reverse. So once I've got this solved, once again, this is just a more complex version where I can sub in for this term right here, this N2O2. Subbing that in, I've just expanded that point out. That's that big term in here. And now I've got just both bromine and K2 to multiply it in. I get this overall one here, where both of those get multiplied into our fraction. We end up with a more complex polynomial. So this becomes the steady state rate equation for this mechanism. This is like DNA to a reaction. This is the fingerprint of the reaction. This mathematical form here is unique to a particular set of steps. And you can use this to say, I measured the rate constant, and I predict the rate constant. I have these two pieces. You use initial rates to measure what the order should be. You measure the hypothetical one by drawing out these steps, and then solving the math behind it. If those two things agree, congratulations, you've solved the mechanism. If they do not, there's no way that the mechanism you drew matches with what you see. The one thing, and again, mechanistic rate equations or mechanistic investigation, there's a general statement that nobody can prove a mechanism. That's absolutely true. Basically, what we're saying is, look, reactions are slippery, uncertainty. You may not ever get it down to 100% certainty, but what you definitely can do is disprove things. You can say that there's no way my data fits this hypothesis. This is why I went into kinetics, is because of any other field, it's the one that gets to sit back and go, nope, 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 nope. You can be definitive in your negativity. So this is how we move this part through. Now there's the last step, why I think the steady state rate equation is so cool. Remember we talked about the first two examples today. We said, first example, reaction is slow in the first step. The second example, the reaction is slow in the second step. Those are two extremes that could happen. The steady state rate equation actually captures both of those extremes. The steady state rate equation is the global truth, the global mathematical solution to any mechanism you draw. What we can do, though, is say, look, I can complete two different possible things. If this is the overall rate equation I have solved, and if I say that K2 is a lot smaller than K minus 1, what does that mean? Which step is big, which step is small in that case? K2 is a lot smaller than K minus 1. What's that kind of like saying? First step is slow or second step is slow?
Second.
Yeah, that's like saying the second step is slow. What I'm saying there is there must be a fast pre-equilibrium, slow second step. If that's true, this here becomes this. All we're saying is if K2 is, if K1 is or K2 is much less than K1, this term doesn't really matter. It simplifies to this point. The denominator gets a lot simpler. If that's the case, now you've got this K minus 1, K1, K this over these two. This is the same thing you get from the pre-equilibrium. Oops. So even though at the very beginning we showed you two possible simplifications to work through, if the first step is slow, look at the first step, write the rate equation. If the second step is slow, assuming pre-equilibrium, you jump in this capital K value. Steady state covers both of those two. Steady state says the overall rate equation would be this, and we can go through and do approximations by saying if k is small, here's how that would simplify. Okay, that's where we're going to stop off for today. We will finish off the last parts of kinetics on Friday.
So I just want to put together a quick pencast talking a little bit more about the application of the steady-state rate approximation and how it can be used to derive or to sort of understand what's going on inside a reaction mechanism. So this is an example we had in class. We're using 2 molecules of NO reacting with bromine to produce products that are 2 molecules of NOBr. And it happens by a 2-step mechanism. First, we have our equilibrium. If you notice, we're defining this as our decomposed equilibrium. We have our K1, our forward rate constant, our K minus 1, the reverse rate constant for this first possible equilibrium. And then we have K2, our product forming step, where we're going on to products where we're using up this intermediate we've generated. So the way that we do this, right, is we're going to start off with this overall rate equation. Now, we're going to actually examine the different reactions that are available. So I'm going to draw them as three discrete steps. So first, what we can think of is there's 2 molecules of NO going to products, that's our N2O2, and that happens by K1, little K1. That's just the forward part of the first equilibrium. The second one is just expressing the reverse. So that's taking the N2O2, going back using K minus 1 to our starting materials, NO2, or 2 molecules of NO. So I'm just explicitly showing these as 2 separate steps. This is why we have our K1 and our K minus 1. We then have our product forming step. This is where we take our intermediates, the N2O2 and bromine, to make our product. And that happens by little K2 to make 2 NOBr. So the specific mechanism, remember these differ for every reaction. The mechanism itself is the fingerprint of a reaction, but they'll have a general form like this. Anytime we have a fast pre-equilibrium and then a second step, you're going to have something that's made up of K1, K minus 1, and K2. What's over here, right, what we react and what we form may change with different mechanisms, but they're all going to have this kind of a 3-step kind of a setup. So that's step 1. We've drawn individual pieces. If you look at the approximation we said, what we're going to do is draw or define the rate of the reaction in terms of this final step. So it's the rate of formation of our product, in this case the rate of formation of this last step over here. So we do that, that's going to be equal to K2 times concentration of N2O2 and the concentration of bromine, Br2. Excuse me, add that there, bromine gas. Now, what's important is, remember, this last step is an elementary step, so by inspection, we're saying it's a bimolecular elementary step, and this would be the rate equation associated with that. We then identify the intermediate. N2O2 is not something that shows up in the overall balanced chemical equation, so that's the intermediate component. This is what we're going to have to derive a term for in order to express what the actual steady-state rate equation is, written in terms of just the starting materials we have up over here. So to do that, that's step 2 now. So step 1, write the rate equation for the last step. Step 2, we need to derive or show some expression, d intermediate dt, where intermediate here is our N2O2, and that is equal to everything that changes its concentration. Now if you notice, the intermediate is involved in this first step. It's formed over here. It's used up in these oversteps here. So we're going to have a positive sign. It's going to be plus our K1 and how it was formed. In that case, it's the NO squared. It's used up, according to the second step, minus K minus 1. And the starting materials there are just our intermediate, N2O2. That's the only thing on the starting material side. And then finally, it's used up according to the last step, minus K2, N2O2, and Br2. Okay. Now with those different pieces, what we're going to have to do is rearrange this, bring them all together, and give us an expression where if we're the statement we're making about the steady state rate equation is that, that this overall rate here is equal to 0. We're saying that all of these different terms, that the relative change of this intermediate over time is 0. I'm not saying that there's not any intermediate, we're just saying that its rate of change is equal to 0. So d intermediate dt equals 0, which allows us to go through and solve for our intermediate. So let's just rewrite this. We're saying that d intermediate into O2 dt, which is equal to 0, is equal to, and the full expression again is our plus K1 NO squared minus K minus 1 N2 O2, and then minus K2 N2 O2 and BR2. So we have to go through and isolate and solve for the concentration of our intermediate here. So we're going to group those terms. We're going to, just with algebra, we're going to bring this together. What this will derive out as is the concentration of this intermediate, N2O2, can be expressed as K1 NO squared over the common terms that had them. That's our K minus 1 plus K2 BR2. So this is now the macro expression, or the term which describes the concentration of our intermediate. Last step 3, that's what we've got here. We've got an expression that has this concentration. So this is our step 3 in our overall part. Step 4, we're going to sub it back into our rate expression. Remember we said that the d product, dt, or the rate, let's just describe it that way, rate of this reaction is equal to K2 times the concentration of Br2 times the concentration of N2O2. So now that we have this expression, we sub it into here. That's just substitution of all those materials. This larger sort of term. So K2 is equal to Br2, and expanding that point, it's just K1 NO squared over K minus 1 plus K2 Br2. That's all of that part here in the middle. Which means the final rate expression here, just by multiplying this, this together, we could show this as K1, K2, NO squared, and then bromine, all on the numerator, and the denominator is what we show over here, K minus 1 plus K2 Br2. So this is what we call the steady state rate equation. It is the expression which describes mathematically how the rate will change given a series of different rate constants in a multiple of different steps, but more importantly how the concentrations of the different starting materials can help or hurt this rate. Like you notice here, bromine, Br2, is on both the numerator and denominator, which means it can both accelerate the reaction, it's proportional to the rate, but it also could be considered inversely proportional to the rate with given different components. So I just want to show one last piece of this. Like if you actually think about it, the steady state rate equation is what we call the true mathematical representation, no matter what step in the sequence is slow. So I'm just going to write that out again. The two different steps that we're entertaining right here look as follows, right? We had step 1, which was 2 molecules of NO react in this equilibrium to give us our N2O2, our intermediate. And that has our forward rate constant, K1, and the reverse rate constant, K minus 1. Then we have step 2, and that's where our intermediate, N2O2, plus bromine, reacts to make our products, 2 molecules of NO-Br. And that's using our K2 over here. When we express it like this, we're not making any statement about which is the rate determining step. We don't really know, right? All we know is we have a two-step mechanism, some equilibrium in the first step and some irreversible reaction in the second step. But we're not making a general statement about which of those two is slow is our rate determining step. And that's the beauty of the steady state approximation. What we're really saying is we can derive a mathematical equation that is general. We don't have to make an assumption about which of the two steps is slow. But the two examples we did before, remember, if we said the first step is slow, what we're really saying about both the size of our k's, but also so this is our first step, this is our second step. This would be the energy profile that we could sort of be looking at, right? This is our coordinate diagram here. So if this is the case, right, remember what we said before is that if this first step is slow, we're saying that the delta G naught, or sorry, delta G double dagger for this first step is much larger than the second step. As a result of that, what we say is that the K1, the value of our forward rate constant, is going to be a lot smaller, many times less than any of the other values that's associated in here. More importantly, especially the K2 value, right? What we're saying is that going in either direction, right? If I'm going to either go forward or backwards, the K values associated with that, K1 and in fact K minus 1, can be construed as being very small. We're also saying that K2 is very big, right? Like we're saying that the second one right here is going to be very large. These are assumptions that we can make based on what we know about how this pathway actually looks. Remember, we said before, what that means is we can look at this as saying if that's the rate determining step under this component, then we'd actually simplify this. This would be considered a forward-only equilibrium. We would only really be considering in this case K1, and the way that we'd now write this, if we knew that this first step was slow, then we would now write this rate equation. We'd say that under that circumstance, rate would be equal to simply that first step, K1 times the concentration of NO squared, right? It's approximately equal to just this first step here driving the bus. But let's go back to the steady state rate equation for a second. We've derived this because we knew the first step was slow, and we've applied that simplification that we discussed at the beginning of today's class. If we show the steady state rate equation again, the one we just solved, we said rate can be equal to K1, K2, NO squared BR2, that's the numerator, over K minus 1 plus K2, sorry, little K2 BR. Now, this is our simplified rate equation after knowing the rate determining step is the first one. Here is the steady state rate equation where we're just not saying which of the steps is slow at this time. This is the general statement where we're not really making any assumptions about if the first step or the second step is slow. So this is why we say it's the general solution to the overall rate in this case. So let's apply this, what we just know about this. We just said if the first step is slow, then we know that K2 is going to be very large, K1 and K minus 1 are going to be much smaller. So look what happens to the denominator. We take the general case right here, or steady state rate approximation. We just said this term, K2, is going to be very large, which means K minus 1 is going to be small. It's not 0, but it's going to be small. Now, this kind of goes back to what we talked about with the acids and bases. If you have a denominator of some term, and it's a polynomial, it's something plus something else. But notice, if this second term here is very large, it's the dominant term, then this denominator can simplify. It's approximately equal to just K2 times BR2. Right? That's like saying if this denominator, hypothetically, if the denominator was 1 plus 50, then, well, that's approximately equal to just 50. We're saying that this part of it over here, the smaller one, is not as relevant. We can approximate the denominator simply as this second term, the large one. So again, I'm not saying that K2 is 0. I'm just saying that, I'm not saying that K minus 1 is 0. I'm saying it's small, in which case this denominator can be simplified as just K2BR. So let's rewrite that again. the steady state rate equation is rate is equal to K1, K2, NO squared, and BR2 on the numerator. Denominator full term is K minus 1 plus K2BR. And if K2 is large, which what we're really saying there is step 2 is fast, then we get a simplification. This can be rewritten simply as, we're going to leave the numerator alone, K1, K2, NO squared, and BR2 on the numerator. We're saying the denominator can simplify, where this is going to be small relative to the other, so then that is approximately equal to just simply K2BR. Now, because we no longer have a sum of terms in the denominator, we can now simplify. K2 will cancel K2, BR2 cancels BR2, and this can now be rewritten as K1 NO squared. If you notice, that is the same conclusion we drew when we looked at it back over here. By inspection, I can say if I know the first step is rate determining, I can go through and simplify this where this K1 is the dominant form, in which case I can by inspection say the rate equation is approximately equal to this. That's the first thing that we taught us in today's class. What I'm trying to show here is that if you start off and draw the steady state rate equation, you're not making any assumptions about if the first step or second step is slow. We can take that full steady state rate equation and then apply our simplification. Now we say, okay, given the full steady state rate equation, what if the first step was slow? Then this is the simplification that would follow from that. And we get to the same expressions, the same mathematical form we had before. So there's not multiple different rate equations. What there is the steady state rate equation expresses the overall behavior of the system without any knowledge about the relative magnitudes of K1, K minus 1, or K2. We can then take that steady state rate equation and begin to simplify it, saying if the first step were slow, this is how the steady state rate equation would collapse to give us a more simple form. This is the simplified rate equation under the assumption that the first step is rate determinant. And it applies for the second one too. So let me rewrite that rate equation. So our steady state approximation said K1 equals K1, K2, sorry, let me rewrite that. K1, K2, NO squared, and BR over K minus 1 plus K2 BR2. So if we now had the opposite situation, let's say the first step is fast, the second step is slow. So under this case, first one is here, second step is there. This is the true case where we have a fast pre-equilibrium happening over here, and it's the second step that's a rate determining step. If we draw out our two equations we had before, first step was NO, 2NO, reacting in equilibrium to make NO N2O2, and our second step, N2O2 plus Br, gives us our products 2NOBr. Now, remember when we applied what we called the pre-equilibrium assumption? We said, okay, if this step is fast, the rate determining step is over here. This is our RDS, rate determining step. And in that circumstance, this is our rate controlling step. We have an intermediate, but we can approximate the concentration of the intermediate by assuming that this K1, K minus 1, right, K1 over K minus 1 was approximately equal to our capital K, our equilibrium constant, which gives us some information about the relative population or the terms of these two. That was how we sort of dealt with this. Now we're going to do the same thing, but we're going to start instead using the steady state approximation, right? So to finish off what we said before, if this was a fast pre-equilibrium assumption, how this term would look is we said that, okay, we start with the second term. The rate here is equal to K2, concentration of our intermediate, into O2 and our concentration Br2. That's an intermediate. We know that this rate, if this is under pre-equilibrium assumption, capital K is equal to our K1 over K minus 1, which is equal to, in this case, products are intermediate, into O2 over 2 molecules of NO squared. So that substitution allows us to express this material, the intermediate, as a product of these different components, and we can sub into that. Now, the other way to express it, though, is we're saying, in this case, K2, the second step, is much, 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 much less than any of the other terms than K minus 1. Basically, it's much faster to go back to starting material here than it is to move forward to products if we're starting at this intermediate at this point. So under that sort of case there, K2 is the smallest of our rate constants that we're dealing here. That's the slow step that we're dealing with. So under that case, again, go back up to our steady state approximation. If K2 is the tiny one, and we're saying here is this second term right here is approximately, or can be simplified out. The denominator in the second case is dominated by the larger K minus 1 value. So again, we're not saying that K2 is equal to 0, we're not saying that Br2 is equal to 0, we're just saying that if this value is much, much, much less than K minus 1, then the denominator is approximately equal to only K minus 1. So once again, let me write out the overall rate equation. Rate is equal to K1, K2, NO squared, Br2, over K minus 1 plus K2Br. Br2. Okay. And we said this term here is going to be small relative to our K minus 1. That's an expression, or what we're really saying is that the second step is rate determining, in which case we can rewrite this equation as K1, K2, NO squared, and Br2 over K minus 1. And if you notice this, now these two guys, this ratio here, K1 over K minus 1, that is also like saying capital K, right? The ratio of the forward and backward rate constants, the little k values, is equal to our capital K value. And that equals capital K times K2, NO squared, and Br2. So this is the same mathematical outcome we would get by applying the pre-equilibrium step back over here. If we were to finish the derivation using the pre-equilibrium one, we'd get the same rate equation. So the point I'm trying to emphasize, if you start by deriving the steady-state rate equation, we're not making any predicated guess about which step is slow. We're just solving mathematically how the system should behave. The next two things we can do is say, given a circumstance where either the first step is slow, as we have here, or the second step is slow, as we have here, that steady-state rate equation can simplify into the two other extremes that we've already talked through. So these are all really talking about the same method to derive the same kind of mathematical outcome. Steady-state rate equation is general. The two outcomes, pre-equilibrium, if the second step is slow, versus assuming the first step is slow and then deriving it based off of that. Those are all really the same expression of the same treatment. So I hope that helps a little bit. The most important thing next is to go through, back to your notes. And what we actually have here is a whole series of different mechanisms. If you notice, the overall rate that we're talking here, A plus B makes product plus C. So two starting materials makes two products. And what we're going to show you through in the next couple slides is that we give you a possible mechanism, two steps by which this could happen, and we're not saying anything about which step is the rate determining step. We don't know. So in that case, if there's no information about which is rate determining, we must use the steady state approximation. We have to follow those four steps that we talked through to derive the general rate equation for this system. If you do that, taking this particular disposition, the solution should be this. If you walk through those 4 steps we talked through, deriving as rate equation for the last step, deriving a d intermediate dt, solving for intermediate concentration, and then putting it back in, this is what you should get. So if you notice that this has a particular mathematical formula, K1, K2, A and B. If we change it slightly, notice the difference here for this the second mechanism. It's exactly the same overall reaction, but the mechanism is now different. Now, so here what we have is 2 molecules, A and B, making an intermediate. In the first step, A just made the intermediate. So it's a different reaction in that first path. Once again, we still have a first step, second step, and the rate determining step is unknown. If you follow those 4 steps as we did before, this is the new mechanism you'll get. And take a look. This mathematical form here is not the same as the first example. They have different polynomial form with different things in the numerator and denominator. So what we're really saying is that it will respond differently. Its rate equation looks different, so it'll respond differently to changes in concentration as a different signature of product versus time. The same thing goes for this third one. Now we have a more complicated one where A makes 2 products and then an intermediate recombines with B. Again, different mechanism, steady state rate equation will give you yet another sort of mathematical outcome. So work through each of these. We'll actually post up the longhand solution for each of these derivations, but this is really good practice to work through these 4 steps, the steady state rate approximation, and see if your understanding holds. All right, I hope that helps out.